Visakha, known as the City of Destiny, is spread on the coast of Bay of Bengal in Andhra Pradesh. Being an abode of natural beauty, this city attracts a large number of tourists and is developing by leaps and bounds. Andhra University, which gained national prominence with its unique style of offering higher education, is situated in this city.
Hello everyone. Yes, again, happy to see you all on this Sunday evening. Hello all to this brand new episode of Gita again. I hope you are very excited to listen today's speaker, and I hope today's live session will be also beneficial to you as our previous talks as well. I personally thank Professor PVJD Prasad Reddy Garu, our Honorable Vice Chancellor Garu, for giving this wonderful virtual tech talk platform where experts are coming and sharing their views. And I also thank Professor P. Srinivasrao Garu, our Principal Garu, AU College of Engineering, for helping us to host this virtual tech talk platform where people are getting beneficial by watching these wonderful videos. As initiated by AU College of Engineering, Visakhapatnam, a series of tech talks are being hosted every day at 7 p.m. on Sunday, every Sunday on 7 p.m. Gita provides an online platform for the enrichment of technical knowledge of students of university and other colleges and faculty as well. In this connection, Gita includes technical by domain experts, by faculty and scholars and students to share their expertise and knowledge to the budding engineers and entrepreneurs of India. Gita is being hosted live every Sunday at 7 p.m. And the immense support you are showing is really awesome. We we want more and more support from the audience like you, and I hope this would be a great success only when you people support us. Please share our videos and even our YouTube channel to your friends and family friends so that they get benefited through these videos and help them in shaping their careers as well. So today we have a wonderful speaker. Now I hand over the screen to today's anchor, whose name is Sarvani. Sarvani, the screen is yours now.
Thank you, Vinil. Good evening, everyone. I'm Sarvani. I firstly want to thank Vinil, who gave me this opportunity. As told by him, Tech Talks has been initiated by the university itself, whose chief patron is PVGC Prasad Reddy sir, who is none other than the Honorable Vice Chancellor of the college, and the Professor Pri Srinivas Rao sir is the chairman, who is the principal of the college, and the teacher mentor is Mallikarjun Rao sir, and the student organizer is Vinil. So, coming to today's activity, now I would like to talk about our guests. Dr. Chella Krishnaveer Abhishek is presently a freelancer, emotional linguistic dysplasia pathologist with specialization on microelectronic applications in management. He is currently working as soft skills trainer come faculty in Department of Journalism and Mass Communication, Andhra University. He is a visiting faculty of many reputed institutions. He is the secretary of Center for Emotional Education Society, Visakhapatnam, India. He has received his PhD on Emotional Language Teaching, Department of Linguistic, Andhra University. He has qualified UGC state eligibility test. He is a recipient of 9 master degrees, 20 diploma courses, and he has authored 45 books, 126 articles, research papers, and reviews in various reputed journals and magazines. He won 15 global awards. He visited Blekinge Institute of Technology, Sweden, and has completed courses on sustainable engineering. He has been a part of more than 100 training programs, in invited lectures, workshops, seminars, conferences, and symposiums. He has a music album to his credit, and he has also acted in and directed various award-winning short films. I'm very glad to share about him. Vinil, over to you.
Thank you for the wonderful introduction. Now I hand over the screen to Dr. Challa Krishnaveer Abhishek garu. Uh, the screen is yours, sir.
Thank you so much, Vinil. Am I audible? Am I visible?
Yes, sir. You are audible and visible.
Yes. Thank you. So, thank you so much for the wonderful introduction. So, basically, you might be wondering that I'm coming from humanities background. So, when I'm coming from humanities background, how I became a technocrat. So, basically, now we're in the era of digital humanities, wherein students of humanities or researchers from humanities and students of technology and researchers of technology have to collaborate. So, for example, I'm from linguistics. So, when I try to collaborate with electronics, students of electronics and communication, then the amalgamation gives speech recognition. And for example, I'm a linguist. If I want to collaborate with computer science, it, the amalgamation gives computational linguistics or natural language processing that we do with Python. So, machine learning, artificial intelligence, all these are aspects of interdisciplinary or multidisciplinary works. So I'm an advocate of multidisciplinary research, and most of my research outputs actually focus on this. So I'm talking about microelectronics because I'm currently doing a project along with my co-researcher, who is also my sister. She's Ms. Challa Shushmita. She's a research assistant in University of Louisville, US. So we are together. We are doing. We're working on a paper, a research paper. So before that, actually, when I because my journey began as a student of engineering. I've completed various courses on mobile communications, sustainable engineering, etc. So I understood that when you add social sciences to engineering, then it is complete. So that is the reason why I call myself as digital humanist. So I believe that so all social scientists they have to learn technology, and all technocrats should also learn social sciences like mass communication, political science, sociology, linguistics, law, management, all these aspects. So that's why finally you have the subjects. So coming to microelectronics, this is our research area currently. Me and my sister are working together on microelectronic fabrication. So that's the reason why I've chosen microelectronics as my topic, because I would like to explain microelectronics in a way that a humanities person understands it, or maybe a school student understands it. I believe that when you start with the basics, it will be easy for the receivers or the listeners to understand and comprehend what we're trying to say. Because I'm a soft skills trainer, I talk about the process of communication. I understand the nuances of listening and understanding. So my talk is based on this. So we talk about microelectronics. So we have arithmetic operations, right? We have arithmetic operations like addition and subtraction. So similarly, we have real-time avionic operations like flight operations. So simple arithmetic operation and complex avionic operation. So from simple to complex systems, they comprise of switching devices. So from a simple system to a complex system, both of them comprise of switching devices. So switching devices play a major role from a simple to a complex system. Every system has the switching device. So when we talk about switching devices, we have to come to the basics of understanding how the switching devices are produced. So this is the base of microelectronics or electronics as such. So when you talk about conductors, conductors allow free flow of current. You know that. Insulators, they don't allow free flow of current. So conductors allow free flow of current, insulators don't allow free flow of current. So when you talk about microelectronics, we are actually talking about switching devices which are made using semiconductors. So semiconductors are between conductors and insulators. So when it is on, they allow the free flow of current. When it is off, they don't allow the free flow of current, the free flow of electrons. So semiconductor device is the basic device, is a basic microelectronic device. So we know about conductors, we know about insulators, and between we have semiconductors. So semiconductors are nothing but switching devices that are placed between a conductor and an insulator. So when they're in on state, they act like a conductor. When they're in off state, they act like an insulator. So examples of switching devices are, you have diodes, you have transistors, you have op amps, etc. So these are a few examples of switching devices. So you have electronics. So why microelectronics? Why is it micro? Why is it not macro? So we have to understand that. So my lecture will be based on why micro and why not macroelectronics, and why miniaturization or microing of electronic devices is important is also my topic of interest. So conductor is basically for examples of conductors are metals like copper and gold. The examples of insulators are glass and wood, etc. And the examples of semiconducting devices are silicon, germanium, etc. So this is the basic introduction that I wanted to give you. So you can see nanotechnology fact or fiction. So during 1950s and 60s, there were many different novels and miniature mans, miniature creatures that can enter our body, that can enter our bloodstream. But now, because of microelectronic technology, this is possible. So there are man-made devices which are of the size of red blood cells, that is 10 microns approximately, or 1/10 of your hair strand. Okay, so these are built now. So from fiction, this has become a fact, right? So during 1950s, 1950s and 1960s, there were fictions about traveling within a human body. And now that fiction is a reality. Through microelectronic technology, it is possible, right? So, but now it's a fact. So example, you can see, you have a famous fiction for explaining microelectronics, that is Ant-Man. It's a Marvel series movie. You can see that, you can enter the body, you can enter the bloodstream. Similarly, the microelectronic devices that we are building are able to enter our body and perform complex operations. So why we need small systems? So we need small systems in assisting, especially when it comes to health point of view. It assists in drug delivery, and it helps in conducting minute operations like brain surgeries and heart surgeries. So it actually makes surgeries risk-free, and because sometimes for surgeries you can't use manual hands. So microelectronic devices are of great help in healthcare. So similarly, physiological testing of the functioning of human body can also done with the help of microelectronic devices. So microelectronics, has a lot of applications, and now we need to understand that it is no more a fiction, and it is a fact. So how small is a microelectronic device, or a microelectronic things of microelectronic amplitude? So when we talk about nanotechnology is something which is below 1 micron. 1 micron is nothing but 10 power minus 6 meters. So when a thing is less than 10 power minus 6 meters or less than 1 micron, then it is considered as nanoparticle. So a technology, electronic device that is less than 10 power minus 6 meters is considered into nanotechnology. If it is 10 power minus 6 or more than that, then if the measurement is more than 10 power minus 6 or 10 power minus 6, then it is considered microtechnology. So we know that 1 kilometer is 10 power 3 meters, right? And that is 1,000 meters. 1 millimeter is 10 power minus 3 meters. Similarly, 1 micron, that is when we talk about microtechnology, we measure it in terms of microns. So 1 micron is up to 10 power minus 6 meters. Okay. Similarly, nanotechnology is between 10 power minus 6 to 10 power minus 9 meters. So for example, if you take your hair strand, it can be up to 100 microns. Similarly, dust particles can be from 1 to 5 microns in size. So that's why you can't see them with your naked eye. So similarly, your blood cells, your red blood cells and all, they're up to 10 micron size. Your bacteria is 0.5 micron or 500 nanometers. Okay, your virus is 50 nanometers, your DNA is 20 nanometers, your protein is 10 nanometers, and an atom, the most indivisible object, that is an atom, most indivisible particle, the atom, is 0.5 nanometer. So when we talk about electronic devices, so these electronic devices, because we talk about microelectronics, they are in these ranges, in the ranges of microns. So, for example, the general size of a silicon wafer. So a silicon wafer is basically an unprocessed device. It's like a circuit, where semiconductor devices are stuck on. So that is up to 10 centimeters. So similarly, a microchip, a processed semiconductor device, a microchip, which contains all these processed semiconductor devices, that microchip is actually, its measurement is 1 centimeter. So in 1 centimeter, there are multitudes of transistors, multitudes of diodes, the multiple different triodes. You have different devices, you have resistors, you have capacitors, you have inductors, you have a lot of things in 1 centimeter chip. So within small size, the electronic functionality is carried out. So these small devices even have, when the device itself is so small, when they're in microns and in nanometers and in centimeters. For example, the integrated circuit itself is in centimeters. You can imagine the small microelectronic devices. They might be in, micrometers, macrons, or nanometers. So they'll be very small. So if the device itself is very small, then the values of measurement, you can imagine the values of measurement, they will be very, very minute. So that's why you have pico, femto, and atto. 10 power minus 12 meters is pico, 10 power minus 15 is femto, 10 power minus 18 is atto. So the values of measurement of capacitance and inductance of these small microelectronic devices will be in pico, femto, and atto. That's the reason why we have these values of measurement too. So this is a So there were no semiconductor devices. So, but there were switching devices. There were switching devices, but there were no semiconductor. Semiconductors were not discovered actually. The usage of semiconductors were not understood during this time. So in 1904, so before there were no semiconductor devices. So in 1904, the first diode was built by John Fleming. And similarly, the first triode was built by Lee D. Forrest in 1906. So then also there were switching devices during these times. Also there were switching devices like diodes, triodes, and transistors. So this how can this be achieved without having a semiconductor device? Yes, this can definitely be achieved. For example, you can take the case of a bulb. So this was achieved actually through vacuum tubes. So the best example is bulb. But the main problem with the bulb is basically it is very big and it consumes a lot of space. So it is up to 2 to 4 inches. So it is very difficult. So what happens is in a vacuum tube, during those days when semiconductors were not known, in a vacuum tube, a cathode and an anode were placed. So the cathode is basically high concentration of electrons. And an anode is basically low concentration of electrons and high concentration of holes or positive charge. So because cathode has high concentration of electrons or high density of electrons, it has negative charge. Because anode has low density of electrons, it has a positive charge. So what happens? So we create a vacuum space. During those days, a vacuum space was created within the glass for free flow of electrons without any outside disturbance. So the electrons basically move from high density to low density, right? So the high density is basically cathode, low density of electrons is basically anode. So electrons move from cathode to anode. So in cathode, what we do is we create resistance in cathode to heat it by altering its properties. So by altering its properties, we create a resistance to heat the cathode so that the heat propels some electrons called thermionic emissions. We do this so that the flow of electrons from cathode to anode is constant. So that is the reason why we do this, and so that the electrons move in one direction only. So how do we create a switching effect through this? So basically, we apply voltage. So when we apply positive voltage, the electrons flow from cathode to anode. And according to the convention, the current flows from anode to cathode because current flows in the reverse direction of electrons. That is what the convention that we've adopted. So basically, from cathode to anode, the electrons are flowing and the current is flowing from anode to cathode. So in positive voltage, this happens. Similarly, when you apply negative voltage, then the electrons must now flow from anode to cathode, but this is not possible because in cathode there's a lot of generation of electrons and there's high density of electrons. So now because anode has low density of electrons, the electrons cannot flow from anode to cathode. So thereby what happens is there is no flow of current from cathode to anode because of that, and this leads to the device becoming an insulator. So when there is positive voltage, the device works as a conductor. When there is negative voltage, the device works as an insulator. So by just reversing the voltage, the device is acting as a conductor and as an insulator. So a switching effect is created. So cathode to anode, it acts as conductor. And anode to cathode, when electrons, because electrons can't move from anode to cathode, by reversing the voltage, you can make the device into an insulator. So by changing the direction of current, we're actually creating a switching effect. So this was how switching effect was created in the olden days, before semiconductors were actually discovered, and the work was before a research on semiconductor was actually commenced. This was actually before the semiconductors. But this is a very complicated process and it consumes a lot of space. So you can imagine a regular bulb itself is 2 to 4 inches. So you can imagine a transistor which is 2 to 4 inches. So if the transistor itself is 2 to 4 inches, then how large will the computer be? So the era of bulky electronics. So the first digital computer, because the switching devices, as I've told you, were pretty big, the digital computer was of the size of an entire room. Because a computer has lakhs and lakhs of transistors, right? So when it has lakhs and lakhs of transistors, and if each transistor is 2 to 4 inches, you can imagine the size of the computer. So because the switching devices were pretty big, the digital computers were actually the size of a large room. They were actually the size of a seminar hall. So which used during those times, the room-sized computer, it used 200 kilowatts of electric power. It consumed 200 kilowatts of electric power. You can imagine 200 kilowatts. And it has 18,000 vacuum tubes. 18,000 vacuum tubes. The cost is basically $500,000 or $5 lakh. The cost of this computer was $5 lakh, and no one could afford it. A lot of space, a lot of time, a lot of money. So the weight of this computer was actually 30 tons or 27,000 kilograms. So, and there were 5 million hand-soldered joints in the computer. So that was during that time, during the start of the 20th century. But now, in the 21st century, we have laptops, which are now in the size of a book, a small book. How is it possible? This is possible through microelectronic technology. So this is possible, as I've told you, with the discovery of semiconductors. So when semiconductors were discovered, the size of the transistors started reducing. Okay, the first semiconductor transistor was built by William Shockley, John Bardeen, and Walter Brattain in Bell Labs. Okay, so the first semiconducting transistor. This was built during 1947 in Bell Labs. So we change when we take a semiconductor device. When we take a semiconductor, we can change the semiconductor into a cathode and also into an anode. So we can change the semiconductor into a cathode that is of high electron concentration, or we can increase the number of electrons in one part of semiconductor, and in other part of semiconductor we can decrease the number of electrons. So the part where the number of electrons are of high concentration in the semiconductor will become the cathode, and the low concentration will become anode. Simple. So this is actually achieved. So the cathode is actually created, the cathode part of the semiconductor is actually created through N-doping. N-doping is actually done with the help of phosphorus. So if you take silicon, if you take the element silicon, if you take the element phosphorus, you'll understand that in silicon's outermost shell, there are actually 4 electrons. In phosphorus outermost shell, there are 5 electrons. So when you dope both of them together during N-doping, what happens is there are 1 extra electron is generated. So imagine doping lakhs of silicons and crores and lakhs of silicon and phosphorus. So you have lakhs and crores of free electrons. So when there are lakhs and crores of free electrons, you have a negative charge. You have high density of electrons and you have a cathode. So through N-doping, cathode is created. So the semiconductor device, silicon has 4 electrons, as I've told you, the phosphorus has 5 electrons, 1 electron extra. So when you dope both of them together, you have 1 free electron. So similarly, if you want to create an anode part of the semiconductor device, so anode means low electron concentration. So low electrons means high number of holes or positive charge. So this can be created, anode part of the semiconductor device can be created through p doping. So p doping is actually done through boron. So as I've told you, silicon has 4 electrons in its outermost shell, whereas boron has 3 electrons. So it needs 1 more electron. So what happens? There is deficit of electrons. So holes are created. So when holes are created, there is deficit of electrons and holes are created, you have positive charge. So in this process, a cathode and an anode is created in a semiconductor device. So the best example is PN diode. Okay. When you talk about transistor, you have PNP transistor. PNP transistor is nothing but it's a combination of PN diode and NP diode. So you have PNP transistor. So transistor is basically 2 diodes. So this is how you are actually creating a semiconductor device. You're making it work as a transistor, you're making it work as a diode. So the beginning of microelectronics revolution. So microelectronic revolution, basically, it began during 1950s. The cost of the transistors during 1950s was actually between $5 to $45, depending on the company and depending on the location. So the transistors cost during 1950s was actually between $5 and $45. It took $5 to $45 to produce the transistors, to buy it. And now the cost of transistors in 2006. So for 1 cent, imagine, for 1 cent, you can get 1 lakh transistors now. So that is how cheap transistors are now because of the advancing technology. So during 1950s, the cost of transistors was between $5 to $45. And now, 2006, we are getting 1 lakh transistors in 1 cent. In 1 cent. You can imagine. So when you talk about the first phase was basically the age of discrete transistors. So discrete transistors means they were not manufactured on one substrate. So they were actually connected using a device like a breadboard. So they were manufactured, the microelectronic devices were manufactured separately and they were connected via a breadboard. So they were discrete because they were not manufactured on one substrate. So, for example, you have this 50 transistor radio. So it has 50 transistors as its name suggests. So 50 transistor radio is built by connecting transistors discretely using a breadboard. You can see the example on the PowerPoint slide. So some additional information. So voltage and current are basically directly proportional in linear devices, as we know that. So voltage and current are directly proportional. There is a linear relation between voltage and current. Okay. So what are the linear devices we have? We have inductor, we have capacitor, and we have resistor. So inductors and capacitors obstruct the direction of flow of the current, whereas the resistor, it obstructs the magnitude of flow of current. Okay. And you have non-linear devices where the relation between the voltage and current is exponential. There is exponential relation. So examples are diodes, triodes, and transistors and op-amps, etc. So these are some examples. So in the second phase of microelectronic revolution, you have integrated circuits. So they were invented in 1959 by Jack Kilby in Texas Instruments Company. Okay, so all the devices were actually built on the same substrate at the same time. So during this time, during this revolution, during this phase, all the devices were built on the same substrate at the same time. So same silicon substrate, they were embedded on the same silicon substrate at the same time. So there was same processing time, same processing environment, same processing temperature, same substrate, and the advantages are same working conditions. The working conditions for building everything is same. You can reduce the time. The same material is used. You can actually reduce the cost. Same substrate. So you can actually reduce the cost again. And working is predictable without distortions. The working of the microelectronic device or circuit that you've built is predictable now, and there's no distortion. And also the size, the most important point here is the size is reducing. So there is size reduction. Okay. So coming to the next slide. So basically microelectronics are advantages because there are advantages because of less size, because of the reduced size. So there are different stages of integrated circuits miniaturization. So in the first phase, the technology was called 10 power minus 4 meter technology. So because the size of the smallest device during this phase was actually 10 power minus 4 meters. So in this time, 60 transistors, we were able to embed 60 transistors into one silicon wafer or one substrate. Okay, so 60 transistors we are able to embed into one silicon wafer or one substrate or chip. So, and the cost was actually $1 per transistor. So it is very costly. Similarly, in second phase, the size of the smallest device or a transistor is actually 10 micron or 10 power minus 5 meter technology. So during this time, 2,300 transistors were able to be accommodated or embedded into one silicon wafer of the same size as previous. Okay, one substrate. And the cost of transistors at this point was 10 cents per transistor. So there is drastic reduction in the cost. In the third phase, you have 90 nanometer technology. So the size of the smallest device was actually 90 nanometers. So it can be a beamer. So here 170 crore transistors could be embedded into one substrate of the same size. And the cost is now drastically down to 1 lakh transistors for 1 cent. So that is the advantage of micro nano technology. So here we are talking about Moore's law. So Gordon E. Moore is the co-founder of Intel, and Moore's law is very famous, I guess. Every engineering student has an idea about Moore's law. So Moore says that in his law, he states that the transistor density on an integrated circuit or a chip, or the number of transistors on an integrated circuit or chip, the integrated circuit or chip has to be in the constant size. The size of the integrated circuit or chip shouldn't change. So with this being a constant, the transistor density or the number of transistors embedded on the same IC chip or same integrated circuit doubles every 12 months. Okay, the law says that the transistor density on an integrated circuit or the number of transistors on an integrated circuit chip, they double every 12 months or they double every year. So this was his prediction during 1965. But this law was actually valid only till 1975. But then during 1975, he had to change his law. He had to modify his law. So he now said that from 1975 onwards, he said that the transistor density on an IC chip or the number of transistors on an IC chip, they double actually every 2 years, not 1 year, every 2 years. So the number of transistors on an IC chip, they double every 2 years according to Moore's law from 1975 onwards. So you can see the curve. This was linear and then it slowly curved because, as I've told you, he had to modify it from 1975 because they were doubling only after 2 years. Every 2 years, they were doubling. So that's how we get 1G, 2G, 3G, 4G technologies. So when the size of the transistors are reducing, you get advanced technologies. So this law is actually still valid. It is valid till the 5G technology that we are using currently. So what is micro nanotechnology? So using tool set of advanced manufacturing processes, the technology through which we prepare or fabricate micro nano devices is micro nanotechnology. So here, friends, we have to understand that micro nanotechnology actually talks about the manufacture of micro nano devices and not the function of micro nano devices. So micro manufacture, the tool set of advanced manufacturing processes, the technology through which we prepare or fabricate micro nano devices is micro nanotechnology. So device functioning is not technology here. Preparing the device is technology. Preparing the device is technology. So when we say that the technology is advancing, so here we say that we have advanced technologies and all. So when we say that the technology is advancing, it means that we are getting the capability of making even smaller devices. According to Moore's law, we are able to accommodate even more transistors, even more microelectronic devices. So it's very important that we have to remember this point, that when we say that the technology is advancing, it means that we are getting the capability of making even smaller devices. So you can see that, the size of your electronic devices is decreasing. It has to decrease, right? It has to be friendly, user friendly. It has to decrease. It has to save your money, save your time, save space. So that is the benefit of micro nanotechnology. So with this, my friends, I'll take a break, a small break, and my co-researcher and my sister, Ms. Challa Sushmita, she will be continuing with the presentation. Just give me 1 minute. Thank you.
Hello everyone, this is Sushmita. I'm researcher at University of Louisville. So I'll be continuing the presentation. So okay. So as we already discussed, like there were various evolution of microelectronics, like starting from vacuum tubes, then we talked about discrete ICs, then integrated circuits. Now the new evolution of microelectronics is MEMS devices. So what is MEMS? It's micro electromechanical systems. It's an integration of mechanical device components and electrical components along with sensors and actuators coming into picture. So, what are the mechanical components that can be incorporated? We can talk about springs, channels, cavities, hinges, anchors, etc. So, and electrical components we have already talked about are diodes and op amps, triodes, everything that we've already talked about. So an IC is completely different from a MEMS device. IC consists of only electronic components, while MEMS device it consists of both electrical and mechanical components. And talking about the different fabrication techniques IC and MEMS, we have two kind, like we can either use the traditional IC fabrication techniques or we can use the more advanced and new techniques that have recently come into picture. So what are the traditional IC fabrication techniques that we can talk about? We can talk about deposition, etching, and photolithography. So these are the three basic techniques used in IC fabrication. Similarly, we can use the same traditional techniques for fabricating MEMS devices, but in more challenging ways. So we can talk about in for MEMS fabrication, we can talk about okay for MEMS fabrication. Hope I was audible till now. I'm sorry, like I didn't wear my earphones. Okay. So, talking about the traditional IC fabrication techniques, which can be as well used for MEMS fabrication, are either we can use additive micromachining like spinning, spray coating, e-beaming, sputtering, oxidation. So, these different techniques are used for deposition of films. And we can use subtractive micromachining processes such as that can be again divided into three types. We can either use mechanical machining like diamond milling, ultrasonic machines, abrasive machining, and we can also use chemical machining processes that can either etch the material such as chemical etching, photochemical etching, electrochemical etching, and there are other set of machining processes that are both electrothermal and such as laser beam, plasma beam, ion beam etching, and electron beam etching. So, with the combination of these additive and subtractive micromachining processes, we can fabricate our MEMS devices. Apart from these traditional techniques that we have mentioned, We can also use new technologies like Liga that has recently come into place. So Liga is nothing but consists of lithography, electroforming, and molding. So we might be wondering what's the difference between fabricating an IC device versus a MEMS device. What is more challenging that I was previously talking about? The challenging thing is making these mechanical components. Like we are here trying to make cavities, we are trying to make membranes, anchors, gears, and different type of mechanical components, and these components have high aspect ratio, that is they are of greater width compared to our IC devices because they have to withstand the mechanical movement, so that so without getting disrupted. So these devices have high aspect ratio, and that is what makes these fabrication of these devices more challenging. Okay, so and also like we have already talked about like let's go to the next slide and then I'll continue. Okay, so we have already talked about making these mechanical components, and let's see what are the applications. These MEMS devices find applications in pressure sensors, accelerometers, gyroscopes, inkjet print heads, and they can even be used for drug delivery in through microfluidic channels, tissue engineering, and implantable sensors. They can be also used in implantable sensors. So here are some images, as you can see, which are some MEMS devices that you can see. Here you can see some microfluidic channels, you can see micro mirrors, and so you can see how small these devices are. They're not even the size of a matchstick, head of a matchstick. So you can compare and try to see how small these devices are and how big application they are able to achieve. So, in today's presentation, I'll be giving a brief on micro mirrors, MEMS devices like micro mirrors and accelerometers. I would be talking about little of their functionality and how better they are compared to the traditional applications. So, here you can see, as we talk about micro mirrors, this is a macro scale representation of its functioning. So let's understand it. Here you can see like a series of mirrors that were attached to magnet, and we are trying to slide a magnet down and create a magnetic field by which these mirror drift according to the magnetic field applied, changing magnetic field applied. So now what we do is we shine light on these mirrors, and these mirrors reflect the light on the projector screen. So thereby these micro mirrors find application in projectors. They are used in digital light projectors. And now taking this to micro scale, these micro mirrors are of the size of 10 microns, and each of this micro mirror represents 1 pixel. So you can imagine how small these micro mirrors are. And you can ask, like we already have an LCD display, liquid crystal display projector, then why we need this digital light projector? So what advantage do we get from these digital light projectors? The advantage is that these digital light projectors have high resolution. You can see that each of these micro mirrors are 10 micron. So the resolution is like close to 10 micron, and these micro mirrors are drifted at a very high speed. Here we are using magnetic field to kind of demonstrate how it happens, but in reality, electrostatic field is what drifts these micro mirrors to different orientations. And you might wonder how these are drifting when they're attached to the silicon substrate, because they drift because of they have these hinges that allow the free movement into different orientations. As we previously mentioned, mechanical components consist of hinges, cavities, and all. So we try to fabricate such kind of hinges that allow different orientation of these micro mirrors. So high resolution is one advantage compared to LCD, and DL projectors also have another advantage, that is high quality and high speed of frame transfer, like very quick. This movement almost takes like microseconds to drift to different orientations. So that is very quick drift of video frames. So you have high quality, high resolution compared to LCD displays, so projectors. So that's the big advantage of using a MEMS projector compared to our traditional projectors. And that's one application. And next application is accelerometers. So we have these movable parts that are moving in this way, and these are these stationary electrodes that are not moving and they are constants, these stationary beams and there are these moving beams. So what is happening? So the capacitance between these two plates is changing with respect to the acceleration of the system. Thereby, this capacitance value it gets stored as the information of the acceleration. So using this differential capacitance is what is the operating principle of these accelerometers. So again, these accelerometers are MEMS devices because they have movable parts. And yeah, we can see like MEMS applications are widespread. They can also be used for drug delivery. They can also be used for carrying out very delicate brain surgeries and and a wide range of applications that you can talk about. And coming to the next slide, and one big question is, where are these micro devices fabricated? We have talked about the microelectronics, MEMS devices. We have talked about the different processing techniques such as additive manufacture, additive micromachining, subtractive micromachining. We talked about photolithography, deposit. But where does all this take place? So there has to be these dedicated clean rooms where microfabrication has to take place. Why? This is because we cannot carry out microfabrication in a general room or a general lab because there are a lot of dust particles, and we when we try to talk about such small micro devices, these dust particles are of the size of our devices and they can interfere with the functionality of our microfabricated device. Therefore, it is important for us to create an environment that is devoid of dust particles, electrical disturbances, smoke, dust, bacteria. Everything has to be cleared out through some pumping system. And such dedicated places where microfabrication takes place are called clean rooms. And there is a classification of clean rooms based on the size of particle it pumps out and the size of particles present in the clean room. So if you take of a class 1 clean room, the minimum size of a particle present, dust particle or any particle present in the clean room would be zero point 0.2 microns. But it doesn't have particles, it doesn't have any dust particles of sizes 0.3, 0.5, 1 micron, 5 micron. All such sizes of particles are pumped out of the clean room. And when we talk about the class 2 clean room, it has like it has particles which are of the size of zero point 0.5 microns, but it is still reliable because it doesn't have it can completely get rid of 1 micron and 5 micron particles. And so on, the classification of the clean room is thus based such that, and here you can see that both a clean room of classification 5 and 6 both has 5 micron uh, dust particles or bacteria. But what's the difference? The difference is in the density of these particles. You can see that ISO 5 has very less density of such 5 micron particles per cubic meter compared to 293 per cubic meter when we take a class 6 clean room. Okay, so this is the clean room classification. And if you are thinking about fabricating the smallest devices, like previously we talked about 90 nanometer technology, there if you're thinking about that, we should have like a class 1 clean room to fabricate such small devices, because any small dust particle or a bug, anything can completely interfere with the functionality of our microfabricated device. So you might wonder, like, we are using these micro devices into our cell phones that are exposed to the environment. So then it has to interfere with the functionality of our devices, right? Since we are using it, but you have to remember that the devices come to us after proper packaging. So the functionality is not affected after it is completely secure, laminated, and packaged. So only during fabrication that these considerations have to be taken care of. Okay, so here is a pictures of a clean room in University of Louisville. You can see that this is like whoever enters the clean room has to wear these bunny suits. They have to cover their heads, they have to cover their hands with gloves, they have to wear masks, they have to cover their feet with dedicated shoes that are present here in the gowning room. They have to wear those. Why? Because we carry a lot of dust with us and we don't want to bring the dust into the clean room, though a lot of it gets pumped out, but we don't want to introduce any dust into the clean room. So it is important that we wear such bunny suits before entering the clean room. And this is the clean room. This is the dedicated place where microfabrication takes place. Here are where these micro devices are fabricated. Here is a Lesker PVD sputtering machine. So this does the additive micro machining that we have previously talked about through sputtering thin films on silicon wafers. And this is a wet etch bay. Here is where subtractive micro machining happens, wherein we try to etch the material through wet etching process. You can see that people working in the wet bench are wearing these PPE. So you might wonder, why is this place so crucial that you have to wear this PPE? Because most of the etchants are acids, and even you have to wear some dedicated gloves, some orange rubber gloves that you have to wear here. So you might wonder why so. This is because most of the etchants are acids, and if they spill on you, it is a very health hazard. So it is care has to be taken such that you wear all the PPE equipment before working in the wet bench. And this is the place where photolithography happens, and where we do the photolithographic patterning is done at these places. This is the photolithography bay, and this is the sus mask aligner. So here is where we place our wafer, here is where we place our mask, and then we shine the UV light to transfer the pattern onto the of the mask onto the wafer. So you can see that here we use a mercury bulb. So we have to be extremely careful because the mercury gas is very poisonous. So there are alarms placed everywhere in the clean room, especially in the photolithography bay, so that if there is any leak, like people are informed and they have to be rushed out of the clean room immediately. So it is very dangerous, as well as it is the most cleanest place also. So you have to be very careful while working in such environments to fabricate our micro devices. So this is a clean room in University of Louisville. Okay. And then we talk about IC fabrication. So as I've already said, so the same techniques of IC fabrication can also be used for MEMS device fabrication. So initially, let's see how IC fabrication is done. Okay. So generally, we know that for IC fabrication we use silicon. Similarly, for MEMS fabrication also we can use silicon substrates. And we can we can grow thin films, as we said, like additive micro machining. And so we can build these thin films on these substrates, either to build the active components such as diodes and everything, or passive components or sacrificial layers that are just used for making the devices and later they are removed. And they can also be, these thin films can also be used for making electrical interconnection between devices. So what kind of thin films are deposited on the silicon wafer? We can think about SiO2 layer, we can think of silicon nitride layer, we can think of epitaxial silicon, we can think about polycrystalline silicon, metal films. So these are the different types of films that get deposited on our silicon wafer for subsequent micro device processing. So, as we previously said, that this silicon is a semiconductor, and its conductive properties are changed locally through either N and P doping. Okay, through N doping is carried out through phosphorus doping, and P doping is carried out through boron doping. And how is this doping done? when we think about an integrated circuit. This is done through the process of diffusion or ion implantation. And thinking about lithography, so lithography is done to transfer an electron device pattern from mask onto a film via a photosensitive chemical called a photoresist. So we try to transfer this pattern onto our thin films wherein we fabricate our devices. And this film is selectively etched away such that the desired pattern of film remains on the wafer. And this process is repeated until the fabrication is complete. Okay. So now let's understand like a step-by-step process of this IC fab or MEMS fab, or yeah. So let's go into details. So initially, we consider an ignot of silicon, which we do. Then we do wafering, and we get our silicon wafer, which is available in various sizes. We generally use 4-inch wafers, but they're available in very big sizes too, like 12 inches too. Okay, so we take our wafer and then we do film formation. This film could be an oxide film, a metal film, a silicon nitride film, whichever is needed for processing our desired electronic device. Okay, and after film formation, we do the lithography to transfer the desired pattern onto the thin film from the mask. So the photo mask contains the desired pattern. And how do we get the desired pattern onto the photo mask? This is done through something called e-beam lithography. So we write the design onto the photo mask through e-beam lithography, and this mask is subsequently used to process our wafers. So a single mask can be used to process like thousands and millions of wafers at a time. So we can use the same mask. If you want the same design to be repeated, we can use the same mask. So once a mask is made, it can be utilized again and again for various wafers. Okay, so we have transferred the desired pattern onto our film, and then we do the selective etching process. And so this etching can be done through various ways. We have like a dry etching, wet etching. In wet etching, again we can do isotropic etching, anisotropic etching. Like isotropic etching is achieved through dry etching, like dry etch through Zactix or XCF2 etching, and anisotropic etching is achieved through systems like DRIE. And but if you want to achieve like a square cavity or a rectangular cavity in a device, so we already mentioned like we have to even sometimes make mechanical components such as cavities. Sometimes, for example, if you think about a microfluidic device, you need to make a channel that is square or a rectangle, like the circumference is rectangle or square. Then you can use like the uh, like then you can use like our anisotropic etching through DRI. But if you wish to have like a tapered edge, then also you can do anisotropic etching, but you have to select a particular crystallographic orientation of silicon wafer which allows a tapered edge. For example, if you want a tapered etching, then a particular crystallographic orientation of silicon wafer along with a particular KOH etchant can give you a tapered like a diamond shaped circumference microfluidic channel. So you can change the shape of the microfluidic channel or MEMS channel through different types of etching processes, different types of crystallographic orientations that you choose, whether dry etch, wet etch, isotropic etch, and anisotropic etch. So you can use these various techniques to achieve your designed MEMS device or IC device. Like generally in ICs, we generally have like we don't have cavities or something. We might not want to do that, but in MEMS device, we really want to have such things. Okay, so we did etching, we did lithography. So these are the basic steps for fabricating any micro electronic device, and these steps might vary, might go up and down by what type of process you have chosen. If you have chosen a lift off, it is different. If you have chosen a chrome etching, it's different. So it varies depending upon the process you choose. And and then next, after etching, like even after film formation and lithography and after etching, sometimes you don't want to do etching, but you want to do like an impurity doping. As we previously said, we might want to create an n-type semiconductor or p-type through ion implantation and diffusion. Sometimes we want to do that impurity doping to create a diode or some other device, and this process repeats. Like this is done with for a first mask and second mask. And so the first mask, you need not have any alignment done, but for this, from the second mask onwards, the wafer has to be perfectly aligned with the mask. So you have alignment marks on the wafer and the mask, thereby you can align them perfectly and fabricate your desired device. And then you have your silicon wafer, which is a processed silicon wafer, which has your devices or MEMS devices or just IC devices. And then you carry out dicing, and you get your die, and then you do packaging so that you convert a die into a chip. And this is like a process flow diagram of how all this happens. So initially consider a silicon wafer, you grow a thin film such as a, here we have considered oxide, then we apply the photoresist layer, then we use the photo mask, and then we as part of the, like light the UV light on it, and then we do etching and remove the undesired parts of the film. And then here we have done doping, like a p-type or n-type doping to create our desired electronic device such as a diode. So this is like a process flow diagram of the same thing, but more pictorially represented. Okay, so that is what can we can get an idea of what when we think of IC fab and or MEMS fab. As we already said, like MEMS fab, as I said, like it has a high aspect ratio that you have to have etch through a lot. See here, the etching is very small, maybe this much, but when you consider MEMS devices, the you kind of have to etch through the entire silicon sometimes. So not the, like to create cavities or holes. So a silicon width is like 500 microns. Sometimes you have to etch through close to 500 microns, so that's a lot of etching. So sometimes the traditional techniques might not be enough, and sometimes you have to like adopt some new techniques such as Liga, as I've previously said. And here I said like these photo marks for ICFAB, they are generally made of quartz. But when you think of new techniques like Liga, the photo mask is made of some PMMA material. And here you I said E-beam, you write the masks through E-beam lithography, but there you use X-ray lithography to write onto the mask. So there are such differences there when you use the new techniques. So yeah, and then coming to, as I previously said, like we write on this mask, right, through various techniques. uh, like I said, like we use e-beam lithography to write the design on the mask. But where do we create this design of our electronic devices? Which software do we use? So we use LEDit software to create our device designs to be written onto the photo mask. Okay, so this LED software has basic structures like a square, a rectangle. You can have a circle, toroid, and you have some basic shapes to create your design. You have different layers to represent different photo masks. And yeah, and you have different, like center alignment. You have boolean operations which you can perform between layers. Yeah, we can achieve your required design using all these operations that are present in this LED software. It's very easy, user friendly, and very easy to understand and learn. Okay, and then coming to, like, even before we talk about the new methods, let's talk about what other materials other than silicon that we can use for, so for our for new microelectronic devices. So for microelectronic devices other than silicon, we can also use elastomers, carbons, biomaterials, quantum dots, hydrogels, and organic conductors. So when when we talk about these new materials which are beyond silicon, why we need new materials? Because silicon is a very hard material. But if you want to implant our micro devices into our body, or if you want to have some wearable technology, so then they have to be like flexible, conformable, and stretchable too. So these substrates such as elastomers are very stretchy, they're flexible. Mhm. And when we talk about quantum dots, why we need quantum dots? So quantum dots are needed for high resolution cellular imaging. They are man-made semiconductor nanoparticles which can help in high resolution cell imaging, and they can be used as optical probes too. And yeah, and when we try aerogels or hydrogels, so these are also of utmost importance in considering materials beyond silicon. So now let's come to the different methods that we can use to fabricate our micro devices onto these new materials. So we can use 3D printing, fuse deposition 3D printing. We can use inkjet or aerosol printing. So how different is this aerosol printing? So aerosol printing can be done on flat surfaces as well as on 3D surfaces. You can print on 3D surfaces. You can print on flexible substrates such as elastomers, as I previously said. So we can use these new materials and new methods to fabricate newer microelectronic devices that are wearable, implantable, flexible, and stretchable too. So, and also we can modify our old materials to behave in new ways. For example, this is a charging wire. Now we have just changed them some using some mechanical processing. We have changed this shape, so now it became stretchable. So we can use newer mechanical processing techniques to achieve it too. And coming to flexible electronics, so as I said, if you want to wear these electronic devices for example, for doing some biomedical sensing or biochemical sensing of sweat and for diagnosis, then we need such flexible electronics, and you can see how these electronics are bent. So what happens? We can either fabricate these devices on our silicon wafer and then transfer onto these elastomer substrates, or we can directly fabricate on these elastomer substrates through processes such as aerosol printing or 3D printing. And next, we can talk about stretchable circuits. So, as I said, instead of silicon substrate, we can use elastomer substrates, or we can even use textile substrates to create our microelectronic devices. Now they are more stretchable, wearable, and breathable too if you are using textile devices. And coming to a more recent, so a 3D printer company in Italy has designed like 100 life-saving respiratory valves in 24 hours. So they use the new 3D printing technique to create these respirator valves. So we can understand that for during this COVID pandemic time, so we can see that our microelectronic technology advances is life-saving too. So I hope our presentation is very worthwhile and we could appreciate the advances and technologies in microelectronics.
Um, the point you said, like very, very important and crucial things that we don't know, like Moore's law, what is micro nanotechnology, and mechanical systems and their applications. And somewhat like I never heard something like silicon. You told something important. Oh, thank you for the today's speech or something like uh, I have some we have some comment sessions in the questions. It is possible to have an image sensor using memes.
Uh, Come again? I'm sorry.
Is it possible to have an image sensor like using memes?
Image sensor? Yes. As we have already said about micro mirrors. I think they are kind of image modulation sensors too. I think they can be used as image sensors too. But that would be a very, I think, vast question. Uh, yeah, I think it's possible.
Yeah.
But we
Thank.
also have like optical MEMS. I think they can be used for image sensing too.
Okay. Okay. Thanks. Thank you. Could we have fabricate DC-DC converters by MEMS?
Okay. I think it's possible because, but I think it's more have to really research upon this question. Uh, but I think since we have our diodes, which we can fabricate diodes, right? So diodes are generally used as rectifiers for like from AC to DC conversion. So, but thinking about DC to DC, I think it's very challenging because we might have to use inductors, and fabricating inductors is very challenging and because they occupy a lot of space. And yeah, I think it has to be possible but challenging.
Okay. Are there any integrated chip fabrication facilities in India?
Oh, I'm not sure about that. Uh,
Yeah.
yeah, there has to be for sure because yeah, there
Okay.
are some many Indian companies and there are clean rooms in India too. So
Oh, okay. Could we employ MEMS for circuit protection?
yeah, yes, surely. Why? Because as we have said, we can like fabricate cavities. So we can fabricate these membranes and like I think like protection films that we can fabricate. I think they can be used for electronic device protection too.
Okay. MEMS for space applications? Can we use them?
Yes, yes, because since I didn't talk about like MEMS antennas, there is a possibility of fabricating MEMS antennas and talking about such micro level technology, we can have like very high frequency uh, communication. So I think it's satellite communication is definitely possible through MEMS.
Okay. Please brief on optical MEMS.
Oh, I really don't know about optical MEMS, so that's not our research this one topic, but
Okay, okay.
yeah.
Thank you.
They're actually
Uh,
working on healthcare. So if there's anything related to healthcare, I think we can clarify because that's our research as topic.
Actually, those were comment sections comment questions I have asked.
Okay.
Vinil, can you please share the screen with us?
Thank you, sir. It was a great lecture, actually, and I hope all the audience of Gita were really beneficial through your lecture. And both ma'am and sir, and we really thank you for your wonderful time and sparing your wonderful time with us. On the whole, it was a very good session, and even the audience have asked some questions, and you answered them pretty well. And we really thank you for your valuable time sharing with us, sir.
Thank you so much for the opportunity. I'm actually sorry for the little inconvenience that I caused because I'm not well, not doing good from past 2 days. So, but at the same time, I wanted to start with basics and then we wanted to proceed on to the advanced applications that we're working on. So, if anybody is interested in healthcare applications, I guess they can definitely contact us. Thank you so much for the opportunity.
Thank you so much.
Thank you, sir. Thank you. I really thank Dr. Challa Krishnaveer Abhishek Garu and his sister for giving such a wonderful speech and wonderful talk about microelectronics and advances. I guess this is a wonderful talk by them, and we will have plenty of talks like these every Sunday at 7 p.m. So please subscribe our channel and do share our channel. And I now thank my professor P. Mallikarjuna Rao Garu for giving this wonderful opportunity. And I also thank Professor Ramachandran ma'am and Computer Cell who has helped us in creating this platform and building this platform and supporting this platform as well. I also thank my team, Chaitanya sir, Gautam sir, Rajesh sir, Mayur, Sarvani, Nitisha and Surya as well for supporting me from the past 2 months in building this and promoting all the videos and all. We will see you on the next Sunday at the same time. So please be stay tuned for to our YouTube channel, and you can also post your suggestions in the comment box below, and you can also write your suggestions and comments to the mail ID given on the screen. So we'll be in touch with you as soon as possible. Please support us and thank you. Jai Hind, Vande Mataram.